Hi, welcome to class. My name is Don LaFon, Professor Don, and this week in Cisco 2, we are covering Module 14, Routing Concepts. The good news is most of this you should already be familiar with, but we'll go through the slides nonetheless. Let me go ahead and share my screen. If you are watching this with me, please hold your questions until the end of the presentation, and I'll give a Q&A period of time where we can chat. If you're watching it as a recording inside of our classroom, please ask your questions inside of our help discussion forums. And if you're watching this on YouTube, please ask questions in the comments section at the bottom underneath the video, and I'll try to stop by, but I do encourage you to answer each other's questions. That's where we can build a community out on YouTube. All right, so we are talking about Module 14, Routing Concepts. I will explain how routers use information in packets to make forwarding decisions, explain how routers determine the best path. We'll explain how routers forward packets to the destination. We'll configure basic routing settings, which we've already done before. We'll describe the structure of a routing table. We'll compare static and dynamic routing concepts, which you should also be familiar with from Cisco 1. Path determination. When a router receives an IP packet on one interface, it determines which interface to use to forward the packet to the destination. This is what's known as routing. The interface that the router uses to forward the packet may be the final destination, or it may be a network connected to another router that is used to reach the destination, the next hop. Each network that a router connects to typically requires a separate interface, but this may not always be the case. The primary functions of a router are to determine the best path to forward packets based on the information in its routing table and to forward packets towards their destination. The router uses its IP routing table to determine which path, route, to use to forward a packet. In this case, R1 and R2 will use their respective IP routing tables to first determine the best path and then to forward their packets. So in this, let me zoom in on this in this picture. So we have we have people on this network and we have people on this network, and we are sending a message from the 168.1.0 network to the 168.0.3 network. And the routers use the routing table to make that determination. And you can see this is router 1, and router 1 is using, to get to the 3 network, it's going to use the 192.168.2.2, in this case, the next hop, which would be this interface. I'm sorry, the next hop, which would be this interface right here. The packet gets the router looks at the routing table and sees the best to get to that network. To get to this network, it must go to next hop 2.2. This is next hop 2.2. That would be 2.1 in the 2.0 network. Yeah, that's how complicated this module is. Of course, we get a little deeper, but that is the concept that we're going to review this week. All right. So the best path in a routing table is also known as the longest match. A routing table contains routing entries consisting of a prefix, network address, and a prefix length, the subnet. For there to be a match between the destination IP address of a packet and a route in the routing table, a minimum number of far left bits must match between the IP address of the packet and the route in the routing table. All it's saying there is the network must be similar, right, or the same. The far left network bits compared to the right, which are host bits. The prefix length of the router in the routing table is used to determine the minimum number of far left bits that must match. The longest match is the route in the routing table that has the greatest number of far left bits, the closest network, matching bits with the destination IP address of the packet. the longest match is always the preferred route. The term prefix length will be used to refer to the network portion of the IPv4 and IPv6 address instead of subnet mask. In the routing table, an IPv4 packet has the destination address IP address of 172.16.0.10. The router has 3 routing entries in the IPv4 routing table that match this packet. It could use the 172.16.0.0/12, the 172.16.0.0/18, and the 172.16.0.0/26. Of the 3 routes, 172.16.0.0.26 has the longest match and would be chosen to forward the packet. For any of these routes to be considered a match, there must be at least the number of matching bits indicated in the subnet mask of the route. So all they're doing here is they're just saying a /26 obviously has more ones or has more matching bits, right? Yes, it just think about the /26 is 111111111, right? It's 26 ones, right? This is the address, but a 26 has 26 ones, an 18 has 18 ones, and a 12 has 12 ones. So if this matches the network, then the 26 is going to be a closest match. An IPv6 packet has in this example has a destination IP address of 2001 DB8 C000::99. This example shows 3 routing entries, but only 2 of them are valid match, with one of these being the longest match. The first 2 routing entries have a prefix length that have the required number of matching bits as indicated in the prefix length. The third routing entry is not a match because the /64 prefix requires a 64-bit match. So 64 requires 64, but 64 does not match. So the 48 would match because it has the longest match. So this would be your choice in the when we're looking at this network. See /48, /64, they don't match. They're not a close match. So we have this is the third one is the best match. Building the routing table. Directly connected networks added to the routing table when a local interface is configured with an IP address of subnet mask and is active up and up. So when you plug a host into a switch and then the switch into the router, it will know the directly connected network. Even if you connect a host into a PC, which is unlikely, but it would still know the network. That's a directly connected network. A remote network, those are networks that are not directly connected to the router. Routers learn about remote networks in 2 ways. You can set them up with static routes. They're added to the routing table when a route is manually configured, or they can learn them dynamically. Dynamic routes are added to the routing table when the routing protocols dynamically learn about a remote networks. And those routing protocols would be OSPF, which they teach you a little bit in this class, very little, or EIGRP or RIP. Those two, those are all found in local networks. Or they could be something like is ISIS or one of the routes that is used by ISPs, but we're not going to talk about those in this class. Those are dynamic routing protocols, and they're, like I said, they're added to the routing table when the routing protocol dynamically learn about them. Default route. That specifies a next hop router to use when the routing table does not contain a specific route that matches the destination IP address. The default route can be entered manually as a static route or learned automatically from a dynamic routing protocol. The default route has a /0 prefix. This means that no bits need to match the destination IP address for this routing entry to be used. If there are no routes with a match longer than 0 bits, then the default route is used to forward the packet. The default route is sometimes also referred to as the gateway of last resort, and that's pretty much the way I call it, the gateway of last resort, the default gateway. You'll hear that term as well. Packet forwarding. Packet forwarding decisions. The data link frame with an encapsulated IP address arrives on an ingress interface. The router examines the destination IP address in the packet header and consults its IP routing table. The router finds the longest matching prefix in the routing table. The router encapsulates the packet in the data link frame and forwards it out the egress interface. The destination could be a device connected to the network, or it could be just the next hop router. However, if there are no matching routing entries, the packet is dropped. That's where the default gateway comes into play. The default gateway would pick up that packet of and it would forward it to the next hop, which is the default gateway, and then it would make a decision of what to do with the packet. All right, so here in our diagram, we have the destination IP address, and it is sent. Let's see, it looks at the routing table, and it looks for the longest match between the destination and routing table. Let me get my, it finds between the entries in the routing table. If there's no entry, if you have not configured a default gateway, then it will be dropped. If it doesn't match anything, it goes from top to bottom. If it doesn't match anything, it will just drop the packet. If it finds something, then it's going to send it to on to the next, either the next hop or the destination, which is on the network. If it knows the address, it sends it directly to the host. If it doesn't know the network, then it sends it to the next hop and then lets that router decide what to do with the packet based on its routing table. Remember, the routing table only has the information about networks it knows about, that is learned in EIGRP. I told you in the first week we were together that if a packet were sent from one side of the country, say in Miami, Florida, to the other side of the country, say Seattle, Washington, your local router in Miami would only know the directly connected and routes that have been learned through EIGRP of the local network or connected networks. That route would not memorize, even though it goes. Your packet is able to go all the way from Miami all the way to Seattle, and then return. Does not mean that router is going to learn all of the hops all the way out to Seattle. All it needs to know is how to send it on to the next router. That next router then makes its decision on where to send it, and on and on and on, all the way it gets out to Seattle. The path is not retained in those routers along the way. The router just learns about the local routers to be able to make educated decisions about where to send. And that's where the EIGRP, RIP, and OSPF come into play, is making those educated decisions based on their routing tables. All right, hopefully that helps a little bit. Okay, keep going. After a router has determined the best path, it could do the following. It can forward the packet to the device on a directly connected network. If the route entry indicates that the egress interface, the interface leaving the router, is a directly connected network, the packet can be forwarded directly to the destination device. Typically, this is on a local area network, maybe connected by a switch with a bunch of hosts connected to it. Or it can encapsulate the packet in the Ethernet frame. The router needs to determine the destination MAC address associated with the destination IP address of the packet. The process varies based on whether the packet is IPv4 or IPv6. Wait, that is directly connected. So in order to send it, it could be sending it, we have to encapsulate it and send it over Ethernet. And remember, we could be sending it to a host that's a wireless host, like a laptop connected to the wireless network, or it could be connected through copper, or it could be connected through fiber as well. So it will reconnect based on the type of connection. It will encapsulate it with the proper type and send it off. Now, after a router has determined the best path, it could do the following. The other option is it can follow. It could, if it isn't on a local network, it can do this. If the route entry indicates that the destination IP address is on a remote network, meaning the device on the network is on a network that is not directly connected, the packet must be forwarded to the next hop router. Then the next hop address is indicated by the routing entry. If the forwarding router and the next hop router are on an Ethernet network, a similar process, ARP or ICMPv6 network discovery, will occur for determining the destination MAC of the packet as described previously. The difference is that the router will search for the IP address of the next hop router in its IP address or its neighbor cache instead of the destination IP address of the packet if it's on its own network. So if it's here and it's forwarding it to a device on the direct network, it's going to do ARP or network discovery for IPv6 and to find the MAC address. If it's on a different network, it's going to look for the IP address instead of the ARP. It's going to look for the IP address in the routing table. This process will vary for other types of layer 2 networks, indicating the type of what it's going to do. Now, after the router has determined the best path, it could also decide to drop the packet if there is no match in the routing table. End-to-end packet forwarding. So the primary responsibility of the packet forwarding function is to encapsulate packets in the appropriate data link type frame for the outgoing interface. I mentioned that a moment ago. For example, the data link frame format for a serial link could be point-to-point, PPT, or HDLC, high-level data link control protocol, or some other layer 2 protocol. That's like from router to router. When the primary responsibility of packet forwarding function is to encapsulate packets in the appropriate data link frame type for the outgoing interface. The more efficiently a router can perform this task, the faster packets can be forwarded to the router. Routers support the following 3 forwarding mechanisms. They can process switching, fast switching, and Cisco Express Forwarding CEF. Now, process switching is an older packet forwarding mechanism still available for Cisco routers. When a packet arrives on the interface, it is forwarded to the control plane where the CPU matches the destination address with an entry in its routing table, and then determines the exit interface and forwards the packet. It is important to understand that the router does this for every packet. Process switching, every packet is evaluated, even if the destination is the same for the stream of packets. That's why it is slowest, and even though it is still used, it is not the preferred method. Now, there's fast switching. Another older packet forwarding mechanism, which was the successor to packet switching, is fast switching. Fast switching uses a fast switching cache to store the next hop information. When a packet arrives on an interface, it is forwarded to the control plane where the CPU searches for a match in the existing in the forward switching cache. If it is not there, then it is process switched like the previous method and forwarded to the exit interface. The flow information for the packet is then stored in the fast switching cache. If another packet going to the same destination arrives on the interface, then the next hop information in the cache is reused without going to the CPU for processing. So in this case, the first packet is processed in the older in the process switching method. So the first packet is process switched and then sent on, but it's also stored in the fast forward cache. You might see it as FFC in the future, fast forward cache. But then if the next packet's going to the same destination, it doesn't need to go through the CPU. It is sent on and on until it reaches the next frame that's not in the fast forward cache, and then it is sent back to the control plane to be processed for the next destination. Now, Cisco Express Forwarding, CEF, the most efficient and also the default Cisco iOS packet forwarding mechanism is CEF. Cisco Express Forwarding builds a forwarding information base, an FIB, and an adjacency table. The table entries are not packet triggered like fast switching, but are change triggered, such as when something changes in the network topology. When a network has converged, the FIB and the adjacency table contain all of the information that a router would have to consider when forwarding a packet. The difference here is this packet switching, the mechanism to determine what's in the FIB is not process switched one at a time like in process switching, or process switched just for the first packet. It is done in advance. So the FIB already has all of the information it needs for all of the networks in the local area, not for the entire internet, right? Just for the local area. It has all of the information that it will need already stored in the FIB, in the adjacency table. Now, once if anything changes, if a router goes offline, it's connected to, or network changes, the OSPF reports a network change, then there is a convergence for the FIB in the adjacency table that takes a bit of time. Once it's complete, then it again has all of the information that it needs. So what we get is all of the processing done early, and then it's a lot less time to process those packets when they enter the router. Basic router configuration review. Again, it's a review. We've done all of this already, but we're going to do it again. We're going to use this topology in the figure for the configuration and verification examples that are going to come. It also will be used in the next topic to discuss IP routing. I have copied this into a couple of the following slides. But what we have is we have 5 networks. We have, and it shows on this network, we have both the IPv4 addresses. We have the 1 network, the 2 network, 3 network, 4 network, and 5 network. We also have the IPv6 networks. Again, we have the 1 network, the 2 network here, 2, 3, 4, and 5. And then actually we have a 6th network here as well, going out to the ISP. Okay, so not too difficult. To configure the router, we have router 1's configuration here. And in router 1's configuration, these are the commands you're going to enter. We've been learning them since the beginning of Cisco 1. So the first basic configuration commands are to give it a name, to set your passwords for both enable, the line console, and the VTY consoles, and then to encrypt all your passwords, and then to enter a message of the day. All of that you've done 50 times, maybe more by this point. Then they're configuring each interface. In this case, we're dealing with router 1. So we're dealing with this router 1, and we're going to configure this interface on 10.0.1.1 and ACAD 1.1. We're going to put on this interface. We're going to add on the it doesn't actually show this is one. It doesn't actually show me. Oh, it is. It is. This is for on S1. It's 3.1. Down here, it's 2.1. All right. Those are these three interfaces. So we go into Ethernet gigabit 000, and we're going to configure 1.1, 64. Then we're going to do configure the IPv6 address. Then we're going to configure a link local address because we don't want it to randomly create a link local address that's hard to remember. So we just create our FE80::1. Don't forget, most important thing, I just skipped it just now, but you do not want to ever skip it, is to enable unicast routing. Otherwise, your IPv4 addresses would work just fine, but none of your IPv6 would work. I've told you that 10 times by now. So we configure G00 for the one network. So we did G0. This is G00. Oh, it says right there, G000. For the one network, here is G001. You can see its configuration for both the IPv4 and IPv6. Notice that we have a link local address configured as well. Don't forget the no shutdown to bring it up. We configure serial for both IPv4 and IPv6 in the local link, and then no shutdown. And then, of course, you have to copy your running configuration to your startup. So if the computer is restarted, then those configurations are retained when the router comes back. When the router restarts, the router configuration is retained. All right. That's it. That doesn't look very hard, does it? No, because you've seen it before. So this is what they consider reviewing router configuration. Now you're going to do oh, I'm sorry. I thought it was going to go in and tell you an assignment to do. I guess we don't get there. So verification command. So we have show IP interface brief, show running configuration interface, show interfaces, show IP interface, show IP route, and ping. And then you replace IP with IPv6 for all of the IPv6 versions. We're going to cover each one of these. I just want to say here at the beginning that the Cisco, the CCNA exam, it will give you on a question, it will say what is the most efficient way to view information about something, whatever that is. And it will give you 4 of these 6 things. And you need to know the differences between show interfaces and show IP interface, for example, and show IP interface brief. You need to know the differences. What would you use to show whether the interface is up? What would be the most efficient way? And in this case, of course, it's show IP interface brief. So let's go through them, and we will, and you're just looking for up and up in that case. Let's go through them. So the first one, it's not going to show you the first one. Oh, no. I'm sorry. I apologize. For what it does is you've seen these interfaces. Matter of fact, I've told you to write these show commands. I've told you to write them into your tech notebook you're definitely your notes, but of course you can't have your tech notebook and your notes when you go to take the exam. So you have to know what each one of these are used for and which one would be the most efficient at each. Now they just say they introduce you to filtering. Filtering allows you to add a pipe command after the show command to then either filter it to a section. You can filter it to include a specific outline that match the filtering expression. You can exclude specific area content that matches, or you can have the display show the lines from, say, a show run or show start. It can start from a specific point that matches the filtering expression. So output filters can be used in a combination with any of the show commands. Those of you that are, let's see, you should be familiar with this if you are familiar with Linux. Linux has the same pipe character to do filtering and also to pipe something into something else in Linux. This is where it says you're going to do a packet tracer indicating or reviewing basic router configuration. Really easy packet tracer at this point. Now let's delve a little bit deeper into the IP routing table. So a routing table contains a list of routes to known networks, prefix and prefix lengths. The source of the information is derived either directly when you connect a host or the switch into the router, static routes, which you've manually configured, or dynamic routing protocols, for example, OSPF, EIGRP, and RIP. The source for each route in the routing table is identified by a code. Common codes include L for those the router interface for directly connected networks, C, the directly connected network, S for static routes that you've input, O for something like for OSPF in this case, and an asterisk indicating that it's a candidate for the default route. That would be your quad zeros in IPv4. There are three routing table principles as described below. These are issues that are addressed by the proper configuration of dynamic routing protocols or static routes on all routers between the source and destination devices. So the routing principle, every router makes its decision alone based on information that it has in its own routing table. R1 can only forward packets using its own routing table. R1 does not know what routes are in the routing table of other routers, for example, R2 or the router of last return. Its default gateway, R1, if it doesn't know where to send something, it's sending it to R2 because it doesn't know where else to send it. Those matching bits aren't there, so it matches 0 bits, so it sends it to its default route. Once it gets to R2, then R2 does the exact same thing. It looks through its routing table to see if it has the information. If it doesn't, it sends it to its default gateway, and on and on and on. The second routing table principle, the information in a routing table of one router does not necessarily match the routing table for another router. Just because R1 has a route in its routing table to a network on the internet via R2 does not mean that R2 knows about the same network. Remember timing. Routes will be removed from the routing table at a predetermined time. So R2 could actually drop the route and R1 might still have the route. So R1 knows the route is on R2. It sends it to R2. R2 doesn't have it, but it then has to do its its processing to determine where the route is, and then it adds it to its routing table. Now, public information about a path does not provide return information. So that was that thing about Miami to Seattle and then back again. A router 1 receives a packet with the destination IP address of a PC and source IP address of PC3. Just because R1 knows to forward the packet out its G00 interface doesn't mean that it knows how to forward packets originating from PC1 to the remote network of PC3. It doesn't know the path all the way from PC1 all the way to PC3, which PC1 could be in Miami and PC3 in Seattle. It doesn't know the whole path. All it knows is to send it on to an interface, the next hop, and then the next hop makes a determination, and on it goes. It never retains the whole path to a destination. I like to explain it as an example from Miami to Seattle, because that would be obvious. It would hit a number of routers, many routers, maybe 10 routers in between. Why would it keep all of that information? Ultimately, you've got to think that a local router, your router on your network, would have a huge routing table if it tried to remember every single PC that it ever connects to, every single host that it ever connects to in the entire universe, right? The whole, not the universe, the entire world, right, on the internet. It would have a huge router. That's not for your router. It's for routers that are higher level to remember those paths to be able to make fast switching on the backbone and stuff like that. So anyways, in the figure, we have the numbers to identify the following. Oh, we break it down. We have the routing source. What are they talking about here? Let me take a look at this. Routing source, how to the route was identified. Okay, so that's one. I should have some numbers here. That's one. This is OSPF. C for directly connected networks. L for the local IP address for that directly connected network, R for RIP, et cetera, et cetera. Then two, this is the destination network that it's going to. Three is the administrative distance. Each network type, OSPF, RIP, EIGRP, directly connected, they all have types of administrative distance, how it was learned. That's the trustworthiness of the route source. For example, one is something that's statically created. The metric that identifies the value assigned to each remote network. Lower values indicate preferred routes, because it's like taking a highway, a 6-lane highway over a dirt road, right? Or that's in one OSPF, for example, but RIP would be just the number of hops between here and there. It could be 5 or 7 or 10 in my example a moment ago. So the metric for RIP, for example, is just the number of hops. And then how is it going to get there? In this case, it's showing the next interface, the next hop IP address, or it could show the exit interface, or it could show both. In this case, it's showing I wish this was all spread out. This is confused. This is IPv6. In this case, it's going next hop interface via serial 011. This is its exit interface. So remember, to get to the next router, it needs to either use its exit interface or the next hop, or both. In this case, it's a fully specified route because they're both there. Now, in the IPv6, I intended to fix this before I would see you again, and I might do that right now. Hang on a second. Let me fix this so I never make this mistake again. Hang on one moment. All right, great. So I went ahead and just took a moment to fix this slide, and I'm going to start the presentation again. All right. So this is a whole lot easier. Oh, I should pull that down a little bit. I'll fix it later, maybe. No, fix it now. All right, I just made a second change, so that's correct. So all to say, it works the same way in IPv6. We have how it was learned. We have the network that we're going to. We have the administrative distance, the metric, the exit interface, serial 001, and or the next hop address. Now, remember from a previous class, you can only use FE80, the local link address, if it's in a fully specified. So you want to be able to use just this address without also giving the exit interface. In this example up here, you could give the exit. You could just do the next hop IP You don't need the exit interface because this is unique. 10.0.3.2 has to be unique on your private network. Not unique in the world, but on your private network, it is unique. There's also a timestamp that identifies how much time has passed since the route was learned. Remember earlier I was saying that routes will time out after a period of time. Again, another mechanism for how the routing table manages routes so that it really can be efficient. If there was no timestamp, it would remember every route it ever learned, which could ultimately end up being a lot of wasted time processing routes that are no longer relevant. All right, so let's keep moving. Oh, it says the prefix length of the destination network specifies the minimum number of far left bits that must match between the IP address of the packet and the destination network prefix of the route to be used, which we covered earlier. Directly connected network. To learn about any remote networks, the router must have at least one active interface configured with an IP address and subnet mask. That just makes sense. You have to connect something to the router for it to then learn about what's out there in the world. This is known as a directly connected network or a directly connected route. Routers add a directly connected route to its routing table when the interface is configured with an IP address and is activated. A directly connected network is denoted by a status code of C in the routing table, as I showed you earlier. The route contains a network prefix and prefix length, the actual network. The routing table also contains a local route to each of the directly connected networks indicated by a status code of L. That's the IP address for the port that it's connected to, the interface on R1 that is configured. I also want to add that only began with iOS 15. If you go back, if you are running a home network to get ready for the CCNA exam, and you're running iOS 12 or earlier, you will not have L's in your routing table. It's only iOS 15 and above. For IPv4 local routes, the prefix length is /32, and for IPv6 local routes, the prefix length is 128. This means the destination IP address of the packet must match all of the bits in the local route for this route to be matched. The purpose of the local route is to efficiently determine when it receives a packet for the interface instead of the packet that needs to be forwarded. I just want to indicate that 32 and 128 indicate one address. That local link address is one address. That's the only thing /32/128 means. It's one address. It's not a network. It's not going on a bunch of addresses. It's just going to one address. And again, it's in the routing table so it can efficiently determine when it needs that interface. Static routes. After directly connected interfaces are configured and added to the routing table, static or dynamic routes can be implemented for accessing remote networks. Static routes are manually configured. They define an explicit path between two network devices. They are not automatically updated and must be manually configured if the network topology changes. Static routes have three primary uses. It provides ease of routing table maintenance in small networks that are not expected to grow. It uses a single default route to represent a path to any network that does not have a more specific match with another route in the routing table. Default routes are used to send traffic to any destination beyond the next upstream router. It routes to and from stub networks. A stub network is a network addressed by a single route, and the router only has one neighbor. If the router has only one network connected to it, it's a stub network. This topology is simplified to show only one LAN attached to each router. The figure shows IPv4 and IPv6 static routes configured on R1 to reach 10.0.4.0 network and the ACAD 4::60/64 network on R2. So again, a static route, the command for IPv4 is, let me turn on my laser, is IP route or IPv6 route. Pretty simple. You're saying here is a route, right? Easy to remember. Here, you got to tell it whether it's IPv4 or IPv6, and then what the network is, and either the next hop IP or the exit interface, or both. In this case, they're just showing the next hop IP address. Same thing down here with R1. It's IPv6 route. Here comes a static route to a specific network. We're going to the 4 network, and we are going to go to the next hop IP address of 3::2. That's the ingress interface in the next hop router. In this case, router 2. You can see it right there. Now, dynamic routing protocols are used by routers to automatically share information about the reachability and status of remote networks. Dynamic routing protocols perform several activities, including network discovery and maintaining routing tables. I'm just looking at that red note there. So here we have that same net topology that we started out the class with. And what it's saying here is in this communication using, for example, OSPF or EIGRP or RIP, in this communication between router 1 and 2, they're just chattering back and forth, sending ND messages and IPv6. Anyways, they're just chattering back and forth, sending information. And what they're saying to each other is, I will share with R2 the networks I know about. And R1 is saying, hey, I will share with R1 the networks I'm familiar with. And so ultimately, R1 learns about these 2 networks, and R2 learns about these 2 networks. And then if there's any changes, then those changes are passed along. Remember earlier we were talking about how a router makes a determination, a packet determination, and it filled its CEF, the database that has all of the information about all the networks, and it only updates that database when there are changes to topology. So this happens, and in the router, CEF configures its information base with all of the routes it knows about, and then from that point on, everything's in that information base. But if there's any change, let's say this disconnects or it goes on a different network, changes the network, then these 2 routers are going to start talking again, and then it's going to update the information base CEF, and it's going to then be updated. That is what happens. Okay. OSPF is now being used in our sample topology to dynamically learn all networks connected to R1 and R2. The routing table entry uses the static code of O, to indicate the route was learned by OSPF routing protocol. Both entries also include the IP address of the next hop router, and it includes it via whatever that next hop router IP address is. IPv6 routing protocols use the link local address of the next hop router, and it also has to have the exit interface if you're using the link local address. So here we look at our IPv4 routing table with the show IP route, and it shows, first of all, it shows all the codes at the top. I love that. And then it indicates that these 2 routes, the 4 network and the 5 network, were learned through OSPF. It cut out the other stuff, the C and the L, because we already learned about that. Down here for seeing the routing table for IPv6, it show IPv6 route. and then it cut out all the directly connected routes, and we see that it learned about these two networks, the 4 and the 5 networks. It learned via the next hop IP address of FE80::2:C and FE80::2. Well, they're the same address but on different networks. And then remember, so you understand why it has to include the exit interface, is that if it didn't include the exit interface, then it would not know where to look here. In this case, I'm going to pause the video and think about this a moment, because I think there might be a mistake on this slide. Hold on. No, there's not a problem with this, because it learned about both of these networks from R2. R2 have these two networks directly connected to R2. So it learned about these two networks through the same next hop IP address on 011 from R1 to R2. That's why they're both the same. There's no problem with that. All right, let's keep going. Default route. So the default route specifies a next hop router to use when the routing table does not contain a specific route that matches the destination IP address. A default route can be either a static route or learned automatically from a default routing protocol. A default route has an IPv4 route entry of we call quad zeros, all zeros, or an IPv6 routing entry of : 0. This means that 0 or no bits need to match between the destination IP address and the default route. Remember, it goes down the routing table looking for a match. If it does not find a match, when it gets to the bottom of the routing table, it will then, you had better have quad zeros down there, otherwise it will drop the packet. IPv4, let's see, so, and they just show, let me zoom in a little bit, they just show that it is going to so R2 would have, could have a default route to R1. R1 could be, this could be configured, I'm sorry, R1 would have a, this could be, I'm sorry, R2 is going to have a route to R1. It could be either static, where you've set it up, or it could be dynamically learned through OSPF, EIGRP, or RIP, for example. Now, R1 is going to have a route to R2. R1's route to R2 could be static. Now, for R1, it would use a default route to R2, because if R1 does not have a path to any address that it wants to reach other than the 1 network and the 2 network, then its default route would be R2. R2's default route is going to be the ISP. If it doesn't want to reach these 2 networks, or these 2 networks, or that network, then it will send all of its traffic to its default gateway or default route to its ISP. If you're missing this path, then these 2 routers can communicate all day with these routes here, but anything that's not going to the 1, 2, 3, 4, or 5 networks would be dropped. And then this is showing the IP route. I wish it had the default route in here, but it would just be quad zeros, and IPv4 would have the asterisks indicating that it is an option for the static route. Structure of an IPv4 routing table. Again, we have gone over that a couple times, but now you're learning a little bit more about it. An indented entry is known as a child route. A route entry is indented if it is a subnet of the class full address of A, B, or C. You can almost always just ignore this address, this line right here. It's really legacy from before we went to um, uh, subnets, and before we had slash 24, 32, all that stuff, right? Now we use these addresses, but you can almost always just ignore that. This is just saying what the network is that all these subnets are on. That's all it does. Directly connected networks begin with a C. L is the local link, the IP address of the router interface on this network. It learned about the 2 and the 3 network from and it dot dot. It would be over here would be the router's next hop address, the interface, exit interface, or both for a fully specified address. And then it goes through the next 2 networks, and that's it. Let's see, the child route will include route source and all the forwarding information for one network. Again, they call them a child route. It's just a network route. The class full network address of the subnet will be shown above the routing entry unless indented and without a source code. This route is known as a parent. Again, you can pretty much ignore the parents. They're not that important. What's important are the networks and the links for each network, how it learned this network, and the next hop IP, the exit interface, or both. Same thing with an IPv6 routing table. And in this case, we have for example, we have a connected network. And to get to that connected network, we go out the 000 network. So the 1 network is on 000. The 2 network is on 001. The 3 network is on 001. Notice at the top there's no parent routes. Again, remember that the parent routes are just a legacy for prior to our slash notation. So you don't have to worry about just no parents. Parents aren't important, right? It's all about the children. I got a couple parents in my class right now who are cringing, right? But in this case, it's true. Parents aren't important. That's what that line is, and you can pretty much ignore it. All right. A couple networks were learned through OSPF down here at the bottom. The administrative distance, a routing entry for a specific network address, prefix and prefix length can only appear once in the routing table. However, it is possible that a routing table learns about some network addresses from more than one routing source, except for very specific circumstances, only one address, the best address, is recorded in the routing table. Only one dynamic routing prototype. It might learn it through multiple ways. You can get from here to there multiple ways, but only one route goes in the routing table, the best route. Remember, I think we learned earlier how you can add a floating route by just adding a number at the end that's higher than whatever your administrative distance is. We might be covering that in a minute, so I won't get too far into that. And I either covered it before or I cover it here in a minute. But anyways, anyways, just the best address, the best route is included in the routing table. So how does the router know which source to use? Which route it should install in the routing table? Well, Cisco iOS uses what's known as administrative distance to determine the route to install into the IP routing table. The administrative distance represents the trustworthiness of the route. The lower the administrative distance, the more trustworthy the route source is. For example, if you plug a switch with some hosts and network into the router, it's pretty much certain that that's the network. So the administrative distance would be 0. If you go in and you type the static route to that network, well, it assumes you know what you're talking about. It's not a 0 because it can't tell by just looking. You had to go in, but it trusts that you're correct. The next one that we using is, or the next one that's using is EIGRP, which is a 90, and OSPF, which is a 110. You need to memorize these numbers. You need to memorize directly connected static route, the 90 for EIGRP, 110 for OSPF, and 120 for RIP. You will get questions that will have those numbers. The other inner routing protocols that you see here, they're for either ISP purposes, or they're no longer used. At least they're not taught in this class. So all you need to know is 0, 1. At this point, all you need to know is 0, 1, 90, 110, and 120. You might not even need to know 120, but they're going to put a multiple choice question together, and they're going to include RIP, which is 120, just to throw you off. So you should memorize them all if you want, and then you'll be better off when you get past CCNA. You'll know if you ever see for example, a 115, which isn't that unusual. You might see an ISIS, but not in CCNA. Static and dynamic routing. So static or dynamic? Static and dynamic routing are not mutually exclusive. Rather, most networks use a combination of dynamic routing protocols and static routes. Static routes are commonly used in the following scenarios. As a default route, forwarding packets to a service provider, the gateway of last resort. When it gets to the bottom of the routing table, it doesn't know where to send it, sends it to the service provider. For routes outside of the routing domain and not learned by dynamic routes, for example, maybe there's a server on a distant route network that you want to be able to have your router always know how to get there. You often send information to that server, then that would be something that would be a dynamic, that would be something that would be a static route. When the network administrator wants to explicitly define a path for a specific network and for routing between stub networks. If you only have one network connected, you set a static route as the default route because it's not going anywhere else on the router. It's only going through that one interface. Static routes are useful for smaller networks with only one path to an outside network. They also provide security in larger networks for certain types of traffic or links to other networks that need control. They call it security, and the reason why OSPF and EIGRP, they're always chattering. They're always talking to each other saying, hey, I know about this network. Hey, I know about this network. Hey, my topology changed. Hey, thanks for sending me that. Or no, I don't know that. Send it to me. So they're always chattering. Well, that if somebody came along and connected to your network through an unsecured path connecting to your console cable and you haven't put a password on it, for example. Anyways, so if it's able to get to your network, then it's able to hear all of that chatter. If it so that is why if you have a static route, then it doesn't. There's no chatter, none at all. You have a static route, it knows where to send it. It does not have to talk to the router next to it to figure out where to send it. Okay. Dynamic routing protocols are implemented in any type of network consisting of more than just a few routers. Dynamic routing protocols are scalable and automatically determine better routes if there are a change in the topology. Dynamic routing protocols are commonly used in the following scenarios. In networks consisting more than a few routers, when a change in the network topology requires the network to automatically determine another path, and for scalability. As networks grow, the dynamic routing protocol automatically learns about any new network. The table below shows a comparison between some of the differences between dynamic and static routing. So, for example, dynamic routing, well, it's easy. The complexity is easy because it automatically scales and changes as the network changes. On the other hand, static network is a pain because any changes to the topology, you have to go in and you have to manually make those changes. Also, if the you add routers, you have to add those manually. So as your network gets more complex, then your static routing becomes more complex. Scalability, I already mentioned. Easy for dynamic, only scalable for simple topologies. So it's not scalable. Or I mean, if you have one router and you add a router, yes, you can implement static routers. But if you have 5 routers and you add 5 routers, now it becomes really complex. Matter of fact, 5 routers is complex. Security must be configured because of all that chatter. On the other hand, static routing, no additional resource because there's no communication, no chatter. It's everything is defined in the from your configurations. Path predictability. The route depends on topology and routing protocol used. In static route, it's explicitly defined by the administrator. What they're saying here is you know what your path is with static routing, but if you have dynamic routing, then you don't know, you don't always know your path because it's automatically determined by OSPF, EIGRP, or RIP. Here is just of evolution on a timeline for each of these routing protocols, and you can see that first of all they were all defined a long time ago. Even though we had RIP version 2, we actually taught all the way up to Cisco NetAcad version 6. It was actually defined back in 1994. So as we're giving this presentation, almost, let's see, 25 years ago, over 25 years ago. Here we have OSPF for IPv6, and we have OSPF here, the upgraded version of OSPF that was initially created. I don't see OSPF 1 on this scale. Whatever. They didn't even bother putting it on here, I guess. Maybe it started with 2. I can't believe that. Here's RIP way back when, but and here's RIP upgraded. EIGRP came along here. And if we're talking about inter ISP routing, ISIS was implemented in 2008. It actually mentions that some basic algorithms for inter-routing protocols were used by ARPANET back as early as 1969. So we've come a long way since then. But these commands that you're going to learn for OSPF and EIGRP, I don't know, they used to teach EIGRP in Cisco 3. We spent a lot of time speaking about EIGRP in OSPF, I'm sorry. We used to teach EIGRP and OSPF in Cisco 3. Now I believe we only teach, we heavily rely on OSPF in Cisco 3, and we touch base on EIGRP and RIP and in Cisco 3. There's no Cisco 4 anymore. Cisco 4 used to be between networks in the ISP. Now that information is included in Cisco 3. All right, this table classifies the current routing protocols. The interior gateway protocols, that's inside your network. Easy to remember. These are inside your network. These are outside your network. Let's see, inside being a single organization, outside being between organizations. There's only one EGP and exterior gateway protocol, and it's BGP. It's used to exchange routing information between different organizations, known as autonomous systems, ASs. BGP is used by ISPs to route packets over the internet. Distance vector, link state, path vector routing protocols all refer to the type of routing algorithm used to determine the best path. For example, distance vector is easy to explain. It's literally the distance, or RIP is super easy. It's the next hop. Link state has to do with more the status of the link. So for example, it's easy to remember like a highway A highway sometimes has a lot of traffic at rush hour, for example. The state of the link is called a highway has gridlock, right? So when you think about taking the highway or the secret back route that nobody knows, that's the state of the link. That is OSPF and ISIS, OSPF version 2 and version 3 for IPv6. The EIGRP and RIP2 just have to do with the RIP is just the number of hops, and EIGRP includes the type of connection as well. So a highway period always is a lower weight or a lower metric than a dirt road, which would be a dial-up modem, right? So it's just concerned with the connection. It's not concerned with the state of the connection as OSPF is. I think that's probably the best I've ever explained it. So you'll have to give me notes down below in the feedback to let me know if that helped you to understand distance vector and link state and which ones are which. Dynamic routing protocol concepts. We continue talking about the concepts. A routing protocol is a set of processes, algorithms, and messages that are used to exchange routing information and populate the routing table with the choice of best paths. The purpose of the dynamic routing protocol includes the following: discover remote networks, maintain an up-to-date routing information in the routing table, choose the best path and only include that best path in the routing table to the destination network, best paths to the destination network in the routing table until there's a change, and then it finds the next best path and puts that into the routing table. The main components of dynamic routing contain data structures. Those are routing protocols typically using tables or databases for their operations. Remember CEF. This information is kept in RAM. Then there's routing protocol message. Those are the routing protocols that use various types of messages to discover. That's the chatting. That's where routers exchange routing information and other tasks to learn and maintain accurate information about the network. And then the algorithm. The algorithm is a finite list of steps used to accomplish a task. Routing protocols are algorithms for facilitating routing information and for best path determination. Remember, an algorithm, you've heard that term before when you're dealing with maybe programming. It's the way we program, the steps to program. You've heard algorithm like Google, for example, has a super algorithm to find 15 billion hits when you type in Ford Mustang, and you get 15 billion hits in a 1 point whatever millisecond search. Well, that's the algorithm that gives it a step ahead of any of its competitions. Routing protocols determine the best path or route to each network. The route is then offered to the routing table. To the routing table. The route will be installed in the routing table if there is not another routing source with a lower administrative distance. The best path is selected by a routing protocol based on the value or metric it uses to determine the distance to reach the network. A metric is a quantitative value used to measure the distance to a given network. I've given you a few hints before now. For example, RIP is just the hop count, how many times it hops. The best path to a network is the path with the lowest metric. Dynamic routing protocols typically use their own routes and metrics to build and update routing tables. The following table lists common dynamic protocols and their metrics. Take a look at that for a moment. So in RIP, I haven't mentioned that the maximum number of hops is 15. So if you have a route with 11 hops, it'll be better than one with 14, but not better than one with 9. Easy enough to know. Open shortest path first, OSPF. The metric is cost, which is based on the cumulative bandwidth of the source to the destination. I always think about faster links of the highway. If you have 6 lanes, it has a bandwidth, the ability to travel. And then EIGRP is a calculates a metric based on the slowest bandwidth and delay values. It could also include load and reliability into the metric calculation. When a router has 2 or more paths to a destination with equal cost metrics, then the router forwards the packet using both paths equally. This is called equal cost load balancing. The router table contains a single destination network, but has multiple exit interfaces, one for each equal cost path. The router forwards packets using the multiple exit interfaces listed in the routing table. If configured correctly, load balancing can increase the effectiveness and performance of the network. Heck, you have 2 paths to the destination, both equally the same. Equal cost load balances is implemented automatically by dynamic routing protocols. It is enabled with static routing, where there are multiple static routes to the same destination network using different next hop routers. Only EIGRP supports unequal load balancing. Now, unequal load balancing would be an example for this would be if you had one path to the destination that uses a highway, right, a fiber connection, but to an ISP. But let's say a company has a backup route as a dial-up router also connected just in case of network failure. Well, unequal load balancing would mean not only would it use the high speed fiber connection, but it would also use the slower connection, and it can be configured that only certain traffic goes through the slower connection. And a good reason to use this unequal cost load balancing is it checks, heck, first of all, you're paying for the dial-up connection, why not use it? But also it ensures that backup is always working. If the backup goes down, you're notified because all of a sudden one of your network paths is not working anymore. And you will be notified of the downed path. If you have things set up properly. If you're not using the backup and it's just sitting there, just not connected, or at least never the main load, and the primary goes down, and somebody maybe has disconnected that backup path or the slower path, then all of a sudden you are down completely because that slower path has not been used and it's no longer valid. So it's not a bad idea to use unequal cost load balancing, especially, and I guess only if you're using EIGRP. All right, so that is module 14. That has been a lot of fun teaching because you guys should know most of that information. If you don't, even if you know the material, I always recommend that you go through the NetAcad content. Remember, if you are out on watching this video on YouTube and you are not in my NetAcad class, you can always go to itanswers.net. itexamanswers.net has all of the content and the videos and animation, all the labs. It's all configured here on itexamanswers.net. I don't get paid by them, but it helps me with you guys that don't have NetAcad because I can send you here to get all of the content. Now, it also has all of the answers, but remember, if you're just using those answers to answer your questions I'm sorry, you couldn't see what I was just doing. I was just showing you itexamanswers.net. But anyways, if you are if you're just using it to answer the questions in the multiple choice exams in my class, that's not helping you to prepare for the CCNA exam. Yes, you will get an A in my class, probably, but you are not preparing yourself for an exam that the answers are not provided for you. Actually, CCNA give you the answers. They're either A, B, C, or D, or actually it could be E, F, G, and H in some circumstances. You'll find when you go to take the exam, you really need to know the material. So using something like itexamanswers.net to answer your multiple choice quizzes in a class is not a good idea. But it does give you the questions and the answers if you're not in a NetAcad course. It gives you all of that information so you can prepare even though you're not part of a class. All right. So my name is Don Lafon, Professor Don. It has been a pleasure to teach you today. If you have any questions and you've got me live right now, please ask your questions. I'll be happy to answer them in just a moment. If you are watching this as a recording, ask your questions inside our NetAcad class, if you're part of my class, in the help discussion forums, or down below in YouTube. Also, please like and review my YouTube videos and follow if you want to be notified when I post additional videos in the future. I really appreciate it if you do that. And I hope you have a great time learning about this information. It is an easy chapter and you will have no problem, I'm sure, learning this material since we've seen most of it before. All right, have a great week and see you next class.